Hello students, in this particular lecture we are going to discuss D block element. In that particular thing we are going to discuss the enthalpy of atomization. What is meant by enthalpy of atomization? We need to understand that. Already I have completed melting point discussion and all. With having that idea we are going to discuss enthalpy of atomization. Enthalpy means energy. So we are converting metal solid into metal atom. What is the meaning? Metal solid means here you have in solid state it is arranged in a fixed arrangement. One metal is attracted by another metal. That force of attraction between the metal is known as metallic bonding. We are giving energy to break this force of attraction, and we are converting metal solid into metal atom in gaseous state. In gaseous state means there will be very negligible force of attraction between metal atom. Here force of attraction is high, here negligible force of attraction, which means they are isolated. Here they are combined state, metal atom is in combined state. Here they are isolated. So for this isolation, for this separation, how much energy is required? That is known as enthalpy of atomization. So enthalpy of atomization is directly proportional to strength of metallic bonding. If metallic bonding strength increases, we need to give large amount of energy. Strength of metallic bonding. Already I have completed the strength of metallic bonding with one more physical quantity, another physical quantity that is known as melting point. So the same variation will be applied here. With having that idea, we are drawing this graph: scandium, titanium, vanadium, chromium. Because chromium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Strength of metallic bonding is directly proportional to number of unpaired electron. Number of unpaired electrons. Scandium configuration 3d1 4s2. So here 3d2 4s2. All the thing will have 4s2, 3d3. Here chromium and copper only having 4s1, 3d5 4s1. Manganese 3d5, 3d6, 3d7, 3d8, copper 3d10 4s1. Here 3d10 4s2. So a number of unpaired electron, 4s having 2 electron means the 2 electrons is paired. There is no unpaired. In 4s orbital, if it is having 2 electron, it is paired. Unpaired illa. 3d1 indicates here it is having 1 unpaired electron. 3d2 indicates 2 unpaired electron. Vanadium 3 unpaired electron. Here in d orbital we have 5 unpaired electron. In s orbital we have 1 electron. So total 6 unpaired electrons. Here 5, 6, 3d6. 3d6. What is the configuration? 1, 2, 3, 4, 5, 6. So number of unpaired electron 4. Here 3 unpaired electron. 3d8 2 unpaired electron. Here in 3D there is no unpaired electron because 3D10 is completely filled configuration. In 4s1 we have 1 unpaired electron. Here 0 unpaired electron. So compared to scandium to titanium, number of unpaired electron increases. If number of unpaired electron increases, metallic bonding increases. Metallic bonding increases, enthalpy atomization increases. That's why scandium to titanium, titanium to vanadium, vanadium to chromium, there will be sudden increase, large increase due to here we have 3 unpaired electron. In chromium we have 6 unpaired electrons. So strength of metallic bonding increases by 3 times compared to vanadium. Vanadium compared to vanadium, chromium has 2 times of strength of metallic bonding. So the variation will be large. On chromium to manganese, it decreases. Actually, the variation is scandium, titanium, vanadium. It is right. Vanadium to chromium, it increases rapidly. Chromium, manganese has lower enthalpy of atomization compared to chromium. But iron has higher enthalpy of atomization than manganese. The reason is again due to its crystal structure. or crystal lattice, due to its crystal lattice. It is because of the manganese-manganese arrangement. In manganese solid, there will be large gap between one manganese and another manganese. If the distance between the atom is large, the force of attraction is small. If the force of attraction is small, by giving small amount of energy, we can break the bond. So here, small amount of energy is needed. That's compared to iron. Even though it has 5 unpaired electron, here only 4 unpaired electron. See, this part is very important. And why zinc is having very low enthalpy of atomization? Because there is no metallic bonding. Because there is no unpaired electron. There is no strong metallic bonding. As all the orbitals are filled, 3d10, 4s2. 3d is also filled, 4s is also filled. So we should understand the variation, why chromium has highest enthalpy of atomization and why manganese has lowest enthalpy of atomization than iron. That is important. Why manganese has lower enthalpy of atomization than iron. This is important. Crystal structure. Okay. And down the group, metallic bonding strength increases. So 4d and 5d and 4d will have higher enthalpy of atomization. Why 5d and 4d will have approximately equal enthalpy of atomization is due to lanthanoid contraction. Okay. With having this idea, we are going to discuss ionization energy. Ionization energy means we have a metal atom. Metals are exist in solid state. By supplying enthalpy of atomization, you convert metal solid into metal atom. From the metal atom, we are going to remove the electron. If you remove one electron from an atom, that metal atom will get positive charge because you are removing one electron. Here, in neutral state, number of electron will be equal to number of proton. That's why there is no charge neutral. Once you are removing one electron, number of proton increases by the difference of 1. So it will be represented by plus 1. You are removing one electron, so it will get plus 1. So for this, how much energy is supplied? That is IE1. IE1 is amount of energy supplied to remove the most loosely bound electron from an isolated gaseous atom. Amount of energy required to remove the most loosely bound electron from an isolated gaseous atom is known as IE1. It will form monopositive ion. This ionization energy otherwise called as ionization enthalpy, or it can be called as ionization potential. The difference is ionization energy, enthalpy, they are exactly same. Ionization potential, definition wise, meaning wise same, but unit wise this will be represented by electron volt per atom. This will be represented by kilojoule per mole. That is the difference. So now we have IE1, IE2, IE3. IE1 means you are removing the electron from an isolated gaseous atom. For this, how much energy is required? IE2 means now you have monopositive ion. From the monopositive ion, you are going to remove one more electron. So already it has 1 plus. Now we are removing one more electron. So it will get, along with 1 plus, it will get one more plus. So it will be plus 2. For this, how much energy is supplied? That is IE2. From dipositive ion, if you are removing one electron, for this how much energy is required? That is IE3. So to define IE1, the amount of energy supplied or amount of energy required to remove most loosely bound electron from an isolated gaseous atom, that is ionization energy, first ionization energy. IE2 is second ionization energy. To define this, the minimum amount of energy required to remove the valence electron from a monopositive ion. So same way dipositive ion this will be. General trend, IE1 is smaller than IE2, IE2 is smaller than IE3. In general, IEN minus 1 will be smaller than IEN. Successive ionization energy will be greater than the predecessor. Clear? So this is about IE1, IE2, IE3. And what are the factors are responsible for ionization energy? What are the factors determine the ionization energy? Factors affecting ionization energy. Effective nuclear charge, atomic size. Ionization energy increases if effective nuclear charge increases. Effective nuclear charge is nothing but the force of attraction which is existing between nucleus and the electron which is going to get removed. Ionization energy decreases with increase in atomic size. They are inversely proportional. So this is about how what are the factors determine the ionization energy. For some cases, we will say the ionization energy is the amount of energy required is small. For some cases, we will say the amount of energy required is large. Why the differences arises? For example, if you take oxygen and nitrogen. Oxygen, nitrogen. Oxygen atomic number 8, nitrogen 7. Air configuration, valence configuration 1s2, 2s2, 2p4, 1s2, 2s2, 2p3. See, according to general trend, across the period, ionization energy increases. So, nitrogen should have higher ionization energy than oxygen. Sorry, oxygen should have higher ionization energy than nitrogen. That is what expected. This is what expected. But experimental was nitrogen is having higher ionization energy than oxygen. This is expected. This is expected. But we are observing this. This is experimental. Why the variations arises? The general trend is nitrogen should have lower ionization energy than oxygen. The reason is here you are removing electron from 2p4. So by supplying IE1, we are removing the electron. Now oxygen will get plus 1 charge. Now the configuration is 1s2, 2s2, 2p3. Here if you remove one more an electron, nitrogen will get plus 1. Here configuration is 1s2, 2s2, 2p2. See, from 2p4 to 2p3. Here 2p3 to 2p2. Now write the configuration separately. P4 to P3, P3 to P2. We know P subshell can accommodate maximum of 6 electron. This is completely filled. Off filled is P3. Completely filled and off filled is more stable than partially filled. Partially filled means P1, P2, P4, P5. This is all partially filled configuration. This is completely filled. This is partially off filled. If the ionization energy you are supplying for converting the system more stable to less stable. Student, this is very important. Ionization energy you are supplying for a system to convert more stable to less stable. In reactant side it is more stable. In product side it is less stable. For this case, we need to give large amount of energy. IE will be I. If the process is converting less stable system to more stable, IE will be small. So less stable to more stable, ionization energy will be small. more stable to less stable, ionization will be large. Now P4 is partially filled, P3 is half filled. Here less stable, here more stable. Most less stable to more stable, ionization energy will be small. P3, here it is half filled, but here partially filled. P3 to P2, more stable to less stable, less stable to more stable, more stable to less stable, less stable to more stable, small, more stable to less stable, large. This is for nitrogen, this is for oxygen. So oxygen ionization energy will be smaller than the nitrogen. This is not the general trend. In periodic table, general trend is ionization energy increases across the period. From left to the right, it should increase. This is what expected, but experimental was this one. Clear? So this is very important. We are going to use this. And one more thing, and one more way to ask question from this concept is, they may ask the number of unpaired electron. Okay. And here S block, D block, P block. In periodic table, we have the arrangement like this: S block, D block, P block. General trend across the period. What should happen? Ionization energy increases. So S block will have lower ionization energy than D block. D block will have lower ionization than P block. This is general variation. Don't forget. Now, ionization energy in 3D series, ionization energy increases gradually with some irregularities. See, it obeys the general trend, it increases, but with some irregularities. Now we are going to account for this irregularities only. Okay. Now one more question can be asked in this type, and by using ionization energy, is number of unpaired electron. Before going to understand how to answer number of unpaired electron question, we should have the idea about after supplying IE, ionization energy 1, the energy gap between n minus 1d and ns will be small. What is the meaning? N minus 1d is nothing but 3d. ns is nothing but 4s. Will be large. Will be large. After supplying ionization energy will be large. If question, see, in neutral state, 3d, 4s, 3d, 1s, 2s, 2p, 3s, 3p, 4s, 3d. This is the arrangement. Once you supplied ionization energy, the orbitals will be separated like this. The energy gap between the orbital will get increased between 3d, 4s. 3d will come to lower energy, 4s will go to higher energy. See, 3d will come to lower energy, 4s will go to higher energy. This transition will happen. This transformation will happen after supplying IE1. How we are going to use this? In this series, scandium, zinc. General trend: scandium should have lower energy, zinc should have higher energy. That is what we observed. But within that, we have titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. We are not observing the general trend here. Even though it increases, the difference is not same. It is not showing any uniformity. We are going to answer for this. So, number of unpaired electron. First, Fe atomic number, ion atomic number 26. Configuration 3d6 4s2. Now, how many unpaired electron present in neutral state? 3d6 means 4 unpaired electron. 3d6 means 4 unpaired electron. Am I right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 4 unpaired electron. After supplying ionization energy, the electron will get removed. It will adopt the Fe+1 configuration. Now, what should we do is count how many electrons present here. Total 8 electrons. From 8 electrons, you are removing 1 electron. So, how many electrons will be there? 7 electrons. Just put all the 7 electrons in 3D. Because the energy difference get increased. Now the electron is not easy to move to 4s. The electron will place in the 3D because energy difference is large. If energy difference is large, electron will not move to the higher energy state. Higher energy state is excited state. It is not a stable state. Electrons wants to be preferred in the lower energy state, that is stable. So 3d7 is a configuration. If 3d7 is a configuration, what is how many unpaired electron? 1, 2, 3, 4, 5, 6, 7. 3 unpaired electron. Usually what we used to do is, see, this is not a correct method. Iron 26 configuration 3d6 4s2. Okay, after supplying IE1, I am going to get the configuration Fe+1. Now 3d6 4s1, we will write this, and below this we will draw the configuration 1, 2, 3, 4, 5, 6. So in d orbital 4 unpaired electron, in s orbital 1 unpaired electron, so total 5 unpaired electron. This is what we usually do. This is not the correct method. Completely wrong. So you should follow this. It's very simple. Just count the number of electron, valence electron. Our usual configuration, no, 3d 4s. How many electrons present there? From that, remove 1 electron. Put all the electrons in 3d. Then count the number of unpaired electron. Now try to do it for Mn to Mn plus 1. How many unpaired electron present in Mn plus 1? Try to do it. Completed? Okay. Next, answer for that question. Mn 25. After supplying IE1, it goes to Mn plus 1. Here configuration 3d5 4s2. Count the number of electron, 7 electrons. So remove 1 electron, configuration will be 3d6. Here number of unpaired electron 5. Here number of unpaired electron 4. Here 5 electron, here 4 electron. If you follow the previous method, the wrong method, your answer will be 6. If you follow this method, this is wrong. If you follow that method, your answer will be 6, because you will remove the 1 electron from 4s. So you will get 4s1 along with 3d5. In 3d orbital 5 unpaired electron, in 4s 1 unpaired electron. So total 6 unpaired electron you will get. That is not correct. 4 unpaired electron is the correct answer. Try to remember this. After supplying IE1, 3d 4s orbital energy difference will be large. Okay. Now we have to compare the ionization energy of manganese and chromium. IE1 of manganese and chromium. Then we have to say which one will be greater. What is the usual trend? Across the period, ionization energy increases. So what is our expectation? Manganese should have chromium manganese. No, okay. Chromium manganese. Manganese should have higher ionization energy than chromium. This is what our expectation. You'll see that one. Chromium 24 configuration 3d5 4s1, right? You are supplying IE1. Here how many electron? 6 electron. Remove 1 electron. Chromium plus 1. Now configuration will be 3d5. Don't consider we are removing electron from 4s. Just add all the electron, then remove the electron. Okay. Chromium, try to remember how to write the configuration. Now come for manganese. Manganese 3d5 4s2 because atomic number is 25. First number is the number of electron present in 4s, second number is the number of electron present in 3d. After supplying IE1, you will get Mn plus 1. Now configuration is here 7 electron. Now it will have 6 electron. Right? Now see here. In 3D it is off filled. In 4 is also off filled. Here it is off filled. Here off filled, full filled, completely filled, but partially filled, which means more stable to less stable. Here this is also stable and this is also stable. So which one will require large amount of energy? Here both are stable. Here this one more stable, this one less stable. So ionization energy of IE1 of manganese will be greater than IE1 of chromium. IE1 of manganese will be greater than IE1 of chromium. First one. Second, compare the ionization energy of chromium and copper and zinc. Pause the video and try to complete it. Copper, atomic number 29, electronic configuration 3d10 4s1. From this I am going to remove one electron, so copper will get the configuration Cu plus 1. Now 3d10. Zinc 3d10 4s2. From this to Zn plus 1 IE1 configuration is 3d10 4s1. Now try to remember here 12 electrons, but don't put 11 electrons in 3d. That is not possible. D can accommodate only 10 electrons. So remaining 1 electron will go to 4s. Our usual technique, we have to add all the electrons, we have to remove an electron, then remaining electron will be placed in 3d. That should not happen here. D can accommodate only 10. Okay. Now here completely filled, which means more stable. More stable to off filled. See here also 3d10, here also 3d10. Here 3d10, here 3d10. So d orbital remains same for all the cases. Here 4s1, here no 4s, which means there is no electron in 4s. 4s will be there. 4s0 is the configuration. Here 4s2 to 4s1. 4s1 to 4s0. For S subshell, S2 is completely filled, S1 is off filled, S0 is no electron in S subshell. S2 is more stable than S1. So S1 to S0, here S2 to S1. This is more stable to less stable. So more stable to less stable, energy required will be large. So ionization energy of zinc will be greater than copper. Now IE2, compare the IE2 of zinc and copper. If you compare the IE2 of zinc and copper, IE2 means we are going to remove the electron from monopositive ion. So Cu plus 1 2, I am going to remove one more electron. So I will get Cu2 plus. From monopositive ion we are going to remove electron. In monopositive ion what is the configuration? Cu plus 1 is 3d10. Zn plus 1 is 3d10 4s1. IE2 Zn2 plus, here 3d10, here 3d9. D10 is completely filled, D9 is partially filled. D10S1, here completely filled, here half filled, but this is stable. 3D10 is completely filled, 4 is no electron. On comparing this to more stable to stable, both are. Here more stable to less stable, because we are getting the partially filled configuration. See, it is a relative property. Why is that? There you took 4s1 to 4s0 requires large amount of energy, but here we are not taking that one. The reason is here comparison between 3d10 to 3d9. There all the 3d having 10 electrons. That's why we are not giving importance for 3d. But here in 3d itself there is change. Here 3d10 is 3d9. So we need to account this. So IE2 of copper will be greater than the zinc. Note down all the things, very important. See, this is a graph, experimentally proven graph. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Scandium, titanium, it increases because atomic size decreases, and it is our correct order. Across the period, ionization energy increases. Why titanium to vanadium it decreases? Why titanium to vanadium it decreases? Titanium 22, 3d2, 4s2. Vanadium 3d3, 4s2, 23 atomic number. I'm going to remove one electron. I'm going to remove one electron. If I remove one electron, what is the configuration? Titanium plus 1. Correct configuration. Here 4. So 3d3. Vanadium plus 1. Configuration. Here 5. So 3d4. Now, see here in 3d3, 1, 2, 3. In 3d4, 1, 2, 3, 4. How many spin exchange is possible? 1, 2, 3. So 3 spin exchange, this 3 unpaired electron can exchange the spin or can exchange the position. So 3 exchanges are possible. Number of exchanges is directly proportional to stability. If more number of exchanges are there, it is more stable. So here 3 exchanges. Here 1, 2, 3. First electron can exchange the spin with other 3 electrons. Second electron can exchange the spin with other 2 electrons. Third electron can exchange the spin with other 1 electron. So 1, 2, 3, 1, 2, 4, 5, 6. 6 exchanges are possible. Here 3 exchanges, here 6 exchanges. Which has more number of exchanges? In vanadium, 3d4 has more number of exchanges. If number of exchanges is more, stability is more. So this is more stable. Compared to here less stable. So here in a titanium case, IE1 lead to the formation of less stable state. In vanadium case, IE1 lead to the formation of more stable state. If it is more stable, if IE1 is used to form more stable, their energy required will be small. If IE1 used to form less stable, the energy required will be large. By using this idea, we can answer this question. Why it decreases here. Clear? And now ionization energy varies group wise, 3D, 4D, period wise, 3D, 4D, 5D. And this is very important thing. 3D to 4D, ionization energy varies down the group. Okay, sorry. 3D series element, 4D series element, 5D series element. General trend down the group, ionization energy decreases. So 3D should have higher ionization energy than 4D. And our expected variation is 4D should have higher ionization energy than 5D. 3D should have higher ionization energy, 4D should have higher ionization energy. But what is the experimental one is 5D is having higher ionization energy than 4D due to lanthanoid contraction. So due to lanthanoid contraction, if you take copper, silver, gold, copper present in 3D, silver present in 4D, gold present in 5D. Our expected variation is copper should have higher ionization than silver, silver should have higher ionization than gold. But the correct variation is copper is having higher ionization energy than silver, but silver is having lower ionization than gold. So correct exact variation is gold is having higher ionization energy than copper, copper is having higher ionization than silver. This is due to lanthanoid contraction. So 3V series, scandium, yttrium, lanthanum. Scandium, yttrium, lanthanum. 3D series, 4D series, 5D series. In lanthanum, there is no lanthanoid contraction. After lanthanum only we are able to observe the lanthanoid contraction. So here correct trend is obeyed. Scandium is having ionization energy than yttrium, yttrium is having ionization energy than lanthanum. 3D series, 4D series, 5D series. See, in 3B alone, our expected variation is observed. In periodic table, scandium, yttrium, lanthanum. This is the arrangement. Below this, actinium will be there. So scandium, yttrium, lanthanum. Here only the observed variation is right. In all other case, 5D is having higher ionization than 3D, 3D is having higher ionization than 4D. This is what observed. In only 3D series alone, in 3B alone, 3D is having higher ionization than 4D, 4D is having higher ionization than 5D. In 3B alone. In the rest of the group, this is what observed. Okay. So with this, we are completing the discussion of ionization energy. In next video, we will discuss density and other parameters. Thank you.